Yes, ma'am.
Okay. So instruction fields, we know that in an instruction format we have an opcode, we have an opcode field, an address field, and a mode field. Okay. So in this we'll be concentrating on an address field. So the number of address fields in the instruction format depends on the internal organization of the CPU. Okay, so it depends upon the internal organization of the CPU. So according to that, there are so many, but among that, the three most common CPU organizations are a single accumulator organization, general register single accumulator organization, general register organization, next stack organization. Coming to single accumulator organization, in this we know about an instruction format. In this we'll be concentrating on address part. Okay, so in an address part, if we have a one address, means like we will be writing an opcode by default. So like which operation we are performing, like whether we are doing addition, subtraction, multiplication, all those. So opcode will be there. So here we'll be concentrating on an address part. So based on a CPU organization, the address part will depends on which one it is using internally. If it is a single accumulator organization, we'll be having a single address. So we'll be having a single address. Okay. So what is this address actually? It is an address which specifies the operand. So here you'll be having a memory. So you'll be having a memory in this, and whatever the address we have here, let us consider 300. So it goes to 300 location, and whatever the data which is there will be executed. Okay, so that is a single address. So I already explained about a single accumulator organization. So whereas in single accumulator organization, one of the operand will be present in accumulator. One of the operand will be present in an accumulator. So here it is mentioned only single address called the second operand. So one of the operand will be automatically, implicitly will be available in an accumulator if you are using a CPU organization. In that, if you are using a single accumulator organization, means if you're performing any operation like addition, adding of two numbers, adding of two operands, one operand by default will be available in the accumulator implicitly. There is no need of mentioning. Okay, so here for that what happens, see here. So one operand will be already present in an accumulator, and the other operand we need to mention the other operand address here. Okay, so add x. So in this we are mentioned an address, so it goes to that particular address called 10 and we'll get a data. Okay, so we after decoding we know that we need to perform an addition operation, and it goes to an accumulator. And if in an accumulator, if it is present called 20, so whatever that we have in an address called x and whatever that we have in an accumulator 20, both will be performed addition based on an opcode what we have mentioned here, addition. So you will be getting the result as 30, and the result will be stored back in an accumulator. See here. So this is a mnemonics for this. See here. Add x. So means what? One of the operand will be available in an accumulator. So it goes to the memory location. X indicates the address of it, specifies the address of an operand. So it goes to that particular address. It will get the operand. It will places that, and in an accumulator we'll be having a 20. Both will be performed an addition. Why? Because we have an opcode called add, and the result will be stored in an accumulator. So this is your single accumulator organization, where in a single accumulator organization, in an instruction format, it will be mentioned only one address. It will be mentioned only one address. So will be called as single that will be called as single accumulator organization. Now let me go for general purpose organization. Okay, so let me clear this. Let me go for a general purpose organization. So in a general purpose organization, while explaining about CPU registers, I said that registers will be of two types. What are those? Can anyone? Registers will be classified into two. What are those? One is
General and one another one is special, ma'am.
Yes, ma'am. Good. So one is a general purpose registers. So one is a general purpose registers, and the other one is a special purpose registers. And the other one is a special purpose register. Why I'm calling this as a special purpose registers is these registers are specially meant for supporting a CPU for execution, like a program counter, an accumulator. So if accumulator means it will be using internally an organization called single accumulator organization. Okay, so general purpose registers are whenever we have any operands present in a memory, whenever we have any operands present in a memory for execution, what we'll be doing is we'll be placing the operands from this memory and we'll be placing in a general purpose registers. So general purpose registers are nothing but we'll be mentioning like R1, R2, R3, like that. Okay, so we will be having only few general purpose registers based on their internal system configuration. So until RL, let us suppose. So what will be stored in this general purpose register is whatever the instruction that we are currently executing, that particular operand after fetching from the memory, the after decoding will be storing inside a general purpose register for execution. So here, so let me see an example. So don't consider that we'll be having only our registers. We'll be having the data from our memory also. So let me show with an example. So let us consider what I'm doing is I'm writing add R1 comma A comma B. Okay, so what did this mean is it also specifies our instruction format means we need to concentrate more on an address field. Opcode by default will be mentioned in same for all the organization, but which we will be getting a difference is in an address field. In a single accumulator organization, it will be mentioned only one address, whereas in general purpose organization, it may be a 2 address or a 3 address. So according to this, you will be having an instruction format in an add place. We'll be having an opcode. We'll be having an opcode, and in an R1, we'll be having a target address. Okay, so we'll be having a target address or target location, and you'll be having operand 1. You'll be having operand 1 address, and you'll be having operand 2 address. Operand to address. Okay, means what we need to go for this. A and B indicates this we need to get the data from memory. R1 indicates this is a register, general purpose registers, which will be present inside a processor for faster execution. So first of all, you based on this instruction format, you will be have according to this example we have 3 addresses. Okay, one is a target one, where what is this target indicates you'll be having a destination, you'll be having a source one, and the other one is source 1 and the other one is source 2. Means what you are taking an operand 1 as source 1 and source 2. We are performing whatever the operation which is mentioned in an opcode. So source 1 is A, so we need to go to the memory location and we need to go to the A location, and whatever that we have in an A address called 100, we got a 10. So we need to take that 10, and next if you go to an address, so here it is not a data, it mentions an operand address. If you go to that address, you will be getting a data. So here again B indicates, let us consider the B is located in an address 100 with a data as 20. So you will be getting A as 10 and B as 20, both will be added, and the result you will be getting as 30. This is your source. This is a destination. After performing an operation called addition, where you have to place in which register, it will be mentioned as R1, or even it may be mentioned with the other memory location as well, like C. Means what after performing an addition, it goes to again a memory location 300 and it places the result 30. Or if it is mentioned as R1, it goes to the registers, it goes to a particular register called R1 and it places the result. So what does this mean is, you in this I'm mentioning an address with three address. So in this we are mentioning three address. An opcode, if it is an accumulator, the format for a single accumulator will be an opcode and an address one. Only a single address of an operand. And when we are performing an addition, how can we perform with a single addresses? Implicitly, one of the operand will be already present in an accumulator. So this address plus the contents of the accumulator both will be performed based on the addition, and then the result will be stored in an accumulator. So the instruction format for a single accumulator organization will be opcode and an address. If it is general purpose registers, you will be having an opcode, address 1, address 2, address 2 and address 3. In this you must know which one is source, which one is destination. Means after performing the operation called opcode, it has to be in which address it has to store, we should be clear. Okay, so these two are the source. We will be going to that particular location, A and B location, will be getting the data, and the result will be storing in a destination called R1 register. This will be calling as three address instruction format, where in an instruction along with an opcode, we are giving extra three address for performing this type of instruction to execute, which is general purpose register. Now let me explain one more, which you can understand even more clearly. See, let me go for add. Okay, so even you can say as add R1 comma A. So don't consider that whenever I am giving any instruction, don't consider that we'll be only getting registers, we'll be only getting memory reference. It may be a combination of memory reference and registers. We already discussed about instruction types. There are three types. What are those three types? Why the instruction may be present in a registers, or it may be present in a memory location, or you can be getting from input output instructions. Okay, so in this, when you are doing an addition, add R1 comma A. So what we are doing is, which one is source, which one is destination, is this both will be considered as source, and the result will be stored again in a destination called R1. Means it go add R1 comma R2 is, it goes to memory location A, and whatever the data it is there will be fetching, will be getting the data. Next, as we have an addition, plus it even adds with the contents of R1. So let us consider, for sake of understanding, in an R1 we got a data as 10. So R1, and in a memory location A called 100, we have a data called 20, let us suppose. So what it will be doing is, in an R1 called 10 and in an M of A, so we have in a register R1 10. So registers will not be specified with an address. Now everyone knows that, right? So registers will not be like a huge in a terabytes, gigabytes. It will be only based on our system's configuration. We'll be having a few, so we'll not be mentioning with a address. So we'll be naming as R1. So it goes to that particular register R1, and we'll be getting the data 10. Okay, so that the value which is the data which is present in R1 and the data which is present in a particular address 20, both will be performed an addition, and it has to store this result. No? So in which it will store means, again this will become a destination. This will become a destination. So it stores the result in R1. It stores the result in R1. This is an example that we can't, but I consider one of the operand as memory so that you can understand even more clearly. See here, add R1 comma R2. These two will become, R1 and R2 will become a source, and again after performing an addition we are storing the result in R1. See here, it adds with R1 contents and R2 contents, both will be added, and after adding it stores the result in R1. It stores the result in R1. So this is, now in this case I want an answer, ma'am. In this case, how many address will be available, ma'am? In this case, in the second one, I completed the first one. In the second one, which I have considered this as an example, so how many address will be available? Can anyone? Code.
Two addresses, ma'am.
Yes, two address. So this will be called as two address instruction format. So we'll be having a target And this also will be having a source. This will be acting as source and target, and this one is source to address. Okay, source to address. But if that is register, we cannot say as a address. Why? Because we'll be giving a name of a registers. So here in this we'll be having two address instruction format. So a single accumulator organization comes under one address instruction format. In a general register organization, we'll be having two types of instructions format called two address instruction format and three address instruction format. Now coming to a stack organization. So when I'm coming to stack organization means the CPU internally, the CPU internally, the instruction format will be considered as zero address instruction format. We'll be using an operation called stack operations for performing a instructions execution. So see here, this is your stack organization. So whenever I'm saying, and I'm only giving an opcode, so instruction format, you'll not mention any address. So you'll be having only opcode. So you'll be having only opcode in a stack organization where we are not giving any address. But what happens if you give an opcode? Whether it may be a subtraction, whether it may be addition. So what happens? Opcode means, let us consider I am writing sub. Okay, now what happens if I am writing sub means whatever we have in a stack, the top, let us consider in this we have uh, in a stack we have a 10 and 20. So what happens, whatever in which will there in the top of the stack, both two operands will be performed and will be performing a subtraction operation, and the result will be popped again in the stack. So in this we are not mentioning any address, but whenever you are pushing, means whenever you want to push any operand into the stack, in that case you will be mentioning an address. See here, push x. Why? Because here whenever you are pushing any operand into the stack, we need to mention an address. So but whenever you are doing an operation other than a push and pop, whenever you are doing an instruction or whenever you are mentioning an opcode, in that you are not mentioning any address. Simply an opcode will be mentioned. But what happens if you mention an opcode means, based on the opcode what we mention, addition, subtraction or multiplication, the top two elements from the stack will be formed and the operation will be performed and the result will be popped back in the stack. This is a stack organization where will be called this stack organization as zero address instruction format. Why I'm saying a zero address is, where in the instruction format you're not mentioning any address, you are only mentioning an opcode. You are only mentioning an opcode. So that's the reason this is zero address instruction format. So according to these three common CPU organizations, we have totally how many instruction formats? Can anyone? According to three CPU organizations, how many instructions format we have?
3, ma'am.
3 or 4? One is in a stack we'll be having a zero address instruction format. In a single accumulator we'll be having a one address instruction format. In a general purpose organization we'll be having a 3 address and 2 address instruction format. So you'll be having a 3 address and 2 address instruction format. So totally we'll be having 4 address instructions formats, starting from 0 address instruction format, 1 address instruction format, 2 address and 3 address comes under general register organization. General register organization. Okay, so based on what type of instruction that we are selecting, based on the type of organization, we will be seeing how it works. So this is a simple organization that we already studied. So we know that a CPU will have a registers and a ALU for execution, and we'll be having a control unit. So and we'll be having a control unit for decoding purpose. After decoding, after finding which opcode it is like, based on that we'll be performing. For that we need to fetch. We need to get the operands and we need to store the results. So for that we are connected this to the memory. So computer instructions are converted into binary codes known as instruction codes. An instruction code is a group of bits that instructs the computer to perform a specific operation. Specific operation. Okay. So we'll start with an instruction format. So an instruction format is a binary format which specifies a computer instruction. See, it specifies the address of the operand, opcode, the addressing mode of the instruction. So we know the instruction format, this instruction format, right? So we have totally 16. So in this from 0 to 11, we'll be placing an address. Address indicates here is what, mark fast. Address here indicates as what? Address is what here. It mentions which address. Specifies the address in, it specifies the
Address of operand.
yes, it specifies the address of operand, what operation it has to perform, and the mode. What is this mode actually? It decides whether it is direct or indirect. So based on this, we can find out the effective address. So if it is 1, the effective address will be where we need to go to that address of address. Then we will be getting an address that will be calling as effective address. So which it decides whether it is direct or indirect. So addressing mode. So now we need to concentrate on this address part. On this address part. So for that, we'll be having totally types of instruction formats. So one is zero address instruction format. So if it is zero address instruction format, it is also called as stack organization, where you will not be having any address. See here, you will not be having any address, a mode and an opcode. So one address instruction format, in a one address instruction format or a single accumulator, will be having one operand. Here operand indicates the address of the operand will be mentioned. So address of the operand. Here in two address instruction format, you will be having operand 1 and operand 2. From this two, both will be performed based on what we mentioned in this. Then the result will be stored back again in a destination address. So this is two address instruction format. Coming to three address instruction format, you will be having an opcode mode. This two will be same, but difference here will be in a address field. So if it is three address instruction format, you will be having a 3. So in this, what happens, ma, can anyone? It goes to operand 1 address, it goes to operand 2 address, and whatever it is mentioned in an opcode called add, both addition will be performed and the result will be stored in which, where, ma?
Destination, ma'am.
Yes, and the result will be stored in a destination address, and the result will be stored in a both based on what opcode it is mentioned in this instruction format, that will be performed, and the result will be stored in a destination register. This is your three address instruction format or a general purpose organization. Two address instruction format also comes under general register organization, general purpose organization. So with one more time, I'm showing it clearly. So common instruction formats, there are 4 which are 0. Now I want, please answer, ma'am. 0 means it comes under which CPU organization?
Stack organization.
Yes, okay, which is a stack organization. Means you will be giving only an opcode, which is this stack. You will be giving only an opcode. Once if you mention an opcode, the top two elements from the stack will be popped, and based on this will be performing an operation, and the result will be pushed into the stack after popping the two elements from the top of the stack. Next, coming to one address instruction format is what, ma'am?
Single accumulator.
Yes, which is a single accumulator, where which one among A, B, C, D? Single accumulator. Okay. So which one is single accumulator means you will be having one address. So this is your single accumulator, where you will be mentioning an opcode and an address. So this address and whatever we have in this address and the contents in the accumulator, both will be performed based on what we mentioned in an opcode, and the result will be stored back in the specified address in an accumulator.
Accumulator, ma'am.
Yes, again the result will be stored back in an accumulator. So this is your one address instruction format. Coming to two address and three address, both comes under
General register, ma'am.
Yes,
General
general
register.
purpose register organization. So this two comes under address 1, address 2, and address 1, address 2, address 3. This is your 2 address instruction format. This is your 3 address instruction format. Is it clear, everyone? Yes, ma. Reply. Is it clear?
Yes, ma'am.
Yes, ma'am.
Yes. Okay. So let me go for 3 address instruction format. Okay, so we have totally 4 types of instructions format: 0 address, 1 address, 2 address, 3 address. I'm starting with 3 address instruction format, where we need to specify 3 address in the instruction format. So here the instruction that I am considered here is x equals to a plus b into c plus d. Okay, x equals to, just a minute. So it is here. Okay, so what is this instruction? X equals to a plus b into c plus d. So let me write this expression here, and x equals to a plus b into c plus d. Is this expression? Yes. Okay, so this I want to do with 3 address instruction format, with using a 3 address instruction format. Okay, so in 3 address instruction format, first what we have to do is we need to mention 3. We'll be having an opcode. We'll be having address 1, address 2, address 3. So address 2 and address 2 contents will be performed based on what operation that we have done and what mentioned in an opcode. Both will be performed and the result will be stored in address 1. So for that what we have here is addition. So let me write add. So let me write add. Next, so these 2 operands are in a memory. So let us consider. So there is one address 100 operand A which is available, and operand B is present in 200, and in this we have a 10, and in this we have a 20. Okay, so this is your memory. This is your memory. This two we need to perform, and whatever that we have mentioned, and the result we are storing inside one general purpose registers. We discussed just now a general purpose registers, which are R1, R2, R3, so on. And whenever you are writing an instruction in a 3 address instruction format, keep it in mind that we need to minimum use of general purpose registers, and the code should be very less. Whatever that you are writing should be optimized one. So it should not be like a lengthy code. So here what we are performing is we are performing an add, and after performing an add, what we want to do is I want to store. We have a 3 address. One is address 1, 2, and 3. This 2 is A and B. This 2 is A and B, and this one is R1. I want to store this result in R1. So I want to use a general purpose register. So this is our target one. This is a target. This is a target register, is where I want to store after performing this operation in the temporary register called R1. So next I need to go to the location A, and I need to go to the location B. I need to perform between 2 addition. So for that, what mnemonics I have to write is, so I need to go for memory location in R1. You're going for memory location A, and plus you are going for memory location B, so that you are getting, after going here, you are getting, okay, you are getting what is A, 10, and B, you are getting the data as, B are getting the data as, what we have
20,
in a
ma'am.
B, 20. Next, the result we are storing in
R1.
the R1. So in R1 we have presently, what we have in an R1, A plus B value, which is nothing but, we have in an R1 A plus B value, which is nothing but 30. Okay, so this is your first. Now, is my instruction completed using 3 address instruction format? This part is completed. Now I need to perform this part. Okay, everyone knows the precedence, and the parenthesis will have a highest precedence, then multiplication and division will have next precedence, which are same. Next lower is addition and subtraction, comes under a lower precedence. So based on that, I have performed A plus B. Next I need to perform C plus D. So for that what I have to do, again an operation called add, and again an operation called add. Next what I need to do, I need to use another general purpose register R2. Why? Because I cannot take R1. Why? Because in R1 we have A plus B. So that is, the result is 30. We are storing in R1. Again, if you take R1, what happens? The A plus B values, what we have done, will be lost. So I am taking one more register R2. And what we have to do, we need to go to C and we need to go to D for getting the operation. So the mnemonics will be, so we'll be having in R2, what we need to store in R2, we need to go to M of C plus, why? Because we have addition. Next M of D. So we need to go to memory location of that particular operand address and we need to get the data. But let us suppose this is also a 10 and 20. So we'll be getting the result in R2 as, so in R2 we will be having C plus D, and that is nothing but 30. This 30 value we are storing in register R1. Okay, register R1. Next is what? I want an answer. Next is what? Can anyone? Next I need to perform a multiplication. So multiplication between the result which is present in R1, A plus B is present in R1, C plus D is present in which register, ma?
R2.
R2. So I need to perform between these two multiplication. Okay. So some what they will be doing is they will be multiplying, and the result they will take one more register called R3. See here, there are so many. Actually, I am not saying that you need to follow this only based on your thinking. You will be having different, but you need to go for optimized one. So you can write like, you can take one more register R3 and you can take R1 comma R2. So what happens, what we have in R1 A plus B, you need to multiply that with C plus D, and the result you are storing in R3. So what is happening in this case, again you are taking that R3 and again you are storing in X instead of that. So what we can do is, so our destination after completing the instruction, where I have to store? In X. Okay, so in memory location X, with where the memory location X address is 100, we need to store the address. Okay, so for that what we need to do is, target address I need to specify, which is X, and where A plus B is present in R1, where C plus D is present in R2. So what is the mnemonics? How can anyone? In M of X, what we are placing? In M of X we are placing R1.
R1 into R2.
Yes, good ma. So in M of X, in the memory location called an address 400, we are doing R1 into R2. Okay, we are performing R1 into R2. So in R1 we'll be having a 30 and in R2 we'll be having a 30, and the result will be stored in a memory location 400. What will be the result?
900, ma'am.
Yes, that 900 will be stored in that particular location. This particular location. So this is your 3 address instruction format. So where you'll be having 3 address. See here, this one, 1, 2, 3. 1, 2, 3. So you'll be having 3 address instruction format. So this is your 3 address. So for same expression, X equals to A plus B into C plus D. If it is 2 address instruction format in a general purpose register, if it is 2 address instruction format, how we'll be writing will be same. Okay, X equals to A plus B into C plus D. First, before going further, think about if it is a two address instruction format, how an instruction format looks like. Answer ma'am. If it is two address instruction format, how an instruction format looks like. First, we'll be having an opcode. Next,
Address 1 and address 2, ma'am.
yes, good. So we'll be having an address 1. We'll be having an address 1 and we'll be having an address 2. We'll be just a minute. Yes, ma'am, am I audible?
Yes, ma'am.
Okay. So we'll be discussing about two address instruction format with the same instruction x equals to a plus b into c plus d. So we'll be having instruction format as opcode address 1, address 2. So for that, what we need to do is, first of all, the operands will be present, whatever A, B, C, D indicates, that will be present inside a memory. So for that, first we need to do moving of those instructions inside a register. So what I'm doing is I'm performing a move. Okay, move which is present in a memory location A inside one register R1. Okay, so here we specified two address. So one is R1 and the other one is A. Means what is performing here is move indicates the address in the memory location. This is your memory location and this is your A address, which is 100, and here you will be having a 10. That 10 will be moved inside a register R1, and previously let us suppose we have in a register 20, that will be overridden and you will be getting as 10 value. So move R1 comma A, the mnemonics for this is what will be, so in an R1 you are moving M of A content. Okay, next after that we need to perform add. Okay, after that we need to perform add R1 comma B. Okay, that means inside an R1, I already said that whenever you are performing an addition, this 2 will become source 1 and this will become source 2, and both will be performed in addition and the result will be stored in register. Means in R1 we have already, in an R1 we have A. In an R1 we have A. Okay, we have an A. Next what we are doing is for that R1 plus we need to go for memory location this B. So we need to go for M of B. So both will be added. So in R1 we have a 10. Let us consider in B address called 200 we have a 10. Okay, so means what, in B location again we'll be having a 10. Both will be added and the result will be stored back in R1. Okay, so this is our first step is we moved one of the operand in general purpose registers with the help of a move opcode. So moving is, it is moving the operand data from a memory location to a general purpose register, which is move. Okay, so move R1 comma A indicates it goes to that memory location, whatever the data is there, that will be moved into R1. This is our target. Okay, here whenever we go for whenever we say add, both R1 contents and the memory location B contents both will be added and the result will be stored back in a R1. Okay, next in an R1, let me write here clearly. Now in an R1 we have what data, ma'am? In an R1 we have,
20, ma'am.
yes, 20 means expression is what? This one, no? Okay, in an R1 we have A plus B, value called 20. Okay, next what we have to do? Can anyone? Please, ma'am. Can anyone? Next step. Move. Next step is what, ma'am? Move.
R2, comma C,
Yes.
ma'am.
Yes, very good. So next one is move R2, comma C. Okay. So the contents of C. So how to write this is, so what is this is, we'll be going to memory location C contents, and those contents we are placing in R2. Why? Because we cannot take R1. In R1 we have a result called A plus B. So we are taking the another general purpose register for called R2, and we are placing the operand which is present in a memory in a general purpose register. So why there is a need of placing the operand which is present in a memory in a general purpose register is execution will become faster. So we moved the C operand which is present in a memory in one of the general purpose register called R2. Then we have to perform add. Can anyone add? Add R2 comma, add R2 comma, what you will be getting, ma'am?
D, ma'am.
Yes, 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 D. So in an R2, what we have in an R2 C, so R2 plus, and we need to go for memory location M of D. So both will be added and the result will be stored in R2. Means in R2 we have let us consider in R2 C value is 10. So we have 10 plus, if you go to M of D we have 5. So both will be added and the result will be stored in R2 again. The result will be stored in R2 again. So we know that in R1 we have A plus B, in R2 we have C plus D. Next we need to perform multiplication between R1 and R2. So this is your R1, this is your R2. Next we need to perform multiplication. So for that next step is what, ma'am?
We
Can
have to
anyone?
take another register, ma'am. R3.
Is it necessary to take another register or mul R1 and R2 is enough? Yes, we can go for simply R1 comma R2. Okay, so in R1 we have A plus B, in R2 we have C plus D. Both will be performed and the result will be stored back in R1. So that's the reason. So whenever you are writing, try to avoid taking general purpose registers more. It should be minimized. So instead of taking R3, you can go for R1 again. You can place inside an R1. So R1, R2, what is this here? In an R1, again you are storing R1 which is A plus B into here. Why? Because it is a multiplication into R2 which is C plus D, and the result is stored in R1. Next step, I want an answer fast. Next, finally, the result is in R1. So we have a result R1 called A plus B into C plus D in R1. Next step is what? We need to store the result in X. For that, what we need to do?
Move operation.
Yes, very good. So we need to write move. What move R1 comma X or X comma R1?
X, comma R1.
R1.
Yes, X comma R1. We have a result in this. This has to be stored inside an X so that it goes to the memory location M of X. Result will be stored in that particular location. So this is your to address instruction format. So whenever you are writing to address instruction format, check that you will be mentioning to address. So here, whenever you are writing, it should be a to. Okay, and in to address instruction format, you will be using a move add like that. So next is what? One address instruction format. This will be discussed.